Welcome to the Explainer. Today, we're doing more than just rattling off a list of commands. We're going to build a really deep, systematic understanding of Linux, especially for anyone in the world of system reliability.
Look, we've all been there, right? We know how to type ls or ps. But to really, truly master a system, you've got to understand what you're actually asking it to do. So, let's move past just memorizing syntax. It's time to start thinking like a senior systems engineer, and that means understanding how our commands are interacting with the very core of the operating system.
You know, the absolute key to mastery is understanding this structure right here. Up at the top, in user space, that's where we live, with our applications and shells. Way down at the bottom, you've got the physical hardware. The real magic, it all happens in the middle. Everything we do in user space has to ask for permission from the kernel to access any resources, and it does that through a super secure gateway called the system call interface. So really, every command is just our way of having a conversation with the kernel, which is the ultimate boss of all the system's resources.
And that is the central idea we have to keep in our heads. The kernel manages everything. Every single command you type is basically a polite request that goes through that system call interface, asking the kernel to do something for you securely and efficiently. Okay, let's really dive into this. So, first things first, we need to be able to ask the kernel what it's busy doing. What work is it currently managing? We're talking about the processes and services that bring the whole system to life. This is always question number one during any incident. What is the system actually doing at this very moment? On any modern Linux system, system control is your go-to for service management. And it's not just some simple script. It's communicating directly with the systemd process. That's the granddaddy of all processes, the very first one started by the kernel, PID1. This makes system control your absolute primary tool for making sure your applications are reliable. And these use cases? They're the bread and butter of our daily work. You check if your web server is healthy with status, that's always your first step. During an outage, you try a quick recovery by restarting it with restart. And, so crucially, you can pull just its logs from the current boot using journalctl. I mean, how powerful is that? No more digging through a mountain of unsorted log files. Now, to look at individual processes, we've got two classic tools. Both PS and top get their info from the /proc virtual file system, which is like opening a window and looking directly at the kernel's live data. The big difference here is that PS gives you a static snapshot, like a photo. Top, on the other hand, gives you a live, constantly updating dashboard. Think of it like a video feed of what's eating your CPU and memory. And this is exactly why these tools are so critical. Imagine this. You're looking at top or maybe MStat, and you see one CPU core is totally maxed out at 100%, while all the others are just chilling. Well, that's the classic sign of a single-threaded application bottleneck. Boom! You've just diagnosed a major performance problem simply because you knew how to read the output. All right, let's switch gears. We need to ask the kernel about storage now. See, it's not enough to know what the system is doing. We also have to know where it's putting its data, and, just as important, how well it's able to get to it. Okay, the File System Hierarchy Standard, or FHS, think of this as a predictable map of the entire system. Just knowing instinctively that config files are in /etc, that logs are always in /vr, and that essential programs are in /bin and /sbin, that's fundamental. This standard map is what lets us write automation and troubleshoot systems we've never laid eyes on before. So when you think there might be a storage problem, IOStat is the tool you reach for. The metrics you really need to watch are latency, that's R08 and W08, and this thing called %IO wait. High latency just means your app is waiting forever for the disk to answer. A high %IO wait, that means your CPU is literally sitting around, twiddling its thumbs, just waiting on that slow disk. That is a classic I/O bottleneck. And check this out. Running IOStat with these exact flags gives you a perfect real-time picture. The X gives you the extended, juicy stats you actually need. The M puts it in megabytes per second, which is way easier to read. T adds timestamps. And the 1.5 at the end? That tells it to update every second for 5 seconds, giving you a live mini benchmark. This is how you catch those super frustrating intermittent disk problems as they happen. Oh man, this error, I think every single one of us has seen this. The reason a tool like LSOF, which just means list open files, can solve it is because of this really elegant idea on Linux. Everything is treated like a file, and that includes network ports. So this command instantly tells you exactly which process is squatting on the port you need, so you can go deal with it. All right, now let's see how we can ask the kernel about its connections to the outside world. Connectivity problems are super common, they can be really tricky, but Linux gives us this amazing toolkit to figure them out. When it comes to network diagnostics, ping is your basic, "Hey, are you there?" check. It sends a little packet and waits for a reply. Simple. But MTR is a true SRE favorite. It combines ping and traceroute into this continuous live view of the entire path to a destination. It shows you exactly which stop along the way is slowing things down or dropping your packets. It's a game changer.
To see what your own server is up to, SS is the modern, super fast command to list all the listening network sockets. Then you can use NC, or netcat, to test if you can actually connect to a port from the outside. And finally, dig is your go-to for making sure DNS is working right. With just these three, you can quickly figure out if the most common causes of a connection failure are the problem.
So let's think about this for a second. All of the tools we've just talked about, they all output one thing: text. So the most critical kind of meta skill for any systems engineer is being able to take all that raw text from logs and command outputs and shape it into real actionable answers.
And these three tools right here are the foundation of all of it. They work together so brilliantly. You use grep to search for and find the lines you care about. You use sed to transform that text. Think of it like a search and replace on steroids. And then you use awk to treat the text like a table, so you can pull out specific columns and even do calculations.
Now, this slide is really interesting because of how it frames these tools with analogies. Grep is your needle in a haystack finder. Sed is like a find and replace brush you can paint across your text. And this last one, thinking of awk as a command line spreadsheet, that completely changes how you approach log analysis. It's not just text anymore, it's data. And this right here perfectly illustrates how these little individual tools can be combined into something way, way more powerful than the sum of their parts. I'm talking about the pipeline, your command line superpower. So here's how it all comes together. We start with journal control to get all the Nginx logs. Could be millions of lines. We then pipe that huge output directly into grep to filter for only the lines that have server errors. Then we pipe that smaller list into awk to pull out just the first column, which happens to be the client's IP address. Finally, we pipe that list of IPs to sort and unique-c to get a perfect count of the top offending IP addresses. I mean, in seconds, we've turned a mountain of log data into a short, concise, actionable report. So the crucial point to take away is this. Linux commands are just a conversation with the kernel. Real mastery doesn't come from memorizing commands. It comes from understanding the system's architecture, the processes, the file systems, the networking, and how to process text. Once you understand what you're asking, you can chain commands together into these amazing pipelines to solve almost any complex problem.
Its power is in its composability. It's the ability to combine simple, focused tools where each one does one thing really well, to build sophisticated, elegant solutions for any problem you can possibly imagine. And that kind of power, well, that's never going out of style. Thanks for joining this explainer.